In last week's lab, you learned about osmosis and the flow of water across membranes. Today, we will be talking about the flow of ions across a membrane and the effect this has on the cell. This flow of ions across a membrane will eventually reach what's called the equilibrium potential. The equilibrium potential is when the electrical driving force completely counteracts the chemical driving force of that ion. Each ion has its own equilibrium potential, which is unaffected by the presence of any other ion. Just like in osmosis, sometimes the membrane is not permeable, so nothing can pass through. Likewise, some membranes can be permeable to one ion but not the other, or permeable to both. To calculate the equilibrium potential of each individual ion, we'll use the Nernst equation. The Nernst equation sets the equilibrium potential of the ion that you're calculating for equal to the 62 log of the ion concentration of the ECF over the ICF. This next slide gives us an excellent example of equilibrium potential. Again, equilibrium potential is when the concentration gradient equals the electrical gradient. Now look closely at this slide. You can see that it's permeable to K only. Try to work this out in your mind of how the concentration gradient can equal the electrical gradient. Now it's time to talk about membrane potential. Membranes of nerve cells maintain a small voltage or potential across the membrane in its normal or resting state. In the resting state, the inside of the nerve cell membrane is negative with respect to the outside due to differences in concentration and permeability of the key ions. Typically, we will see a resting membrane potential of negative 70 millivolts. Plasma membranes of all living cells have a membrane potential. When a membrane potential exists, the unbalanced charges will accumulate in a thin layer along the membrane. The overall membrane potential is created as all of the equilibrium potentials for all of the ions are summed together. As this slide says, this membrane is permeable to both potassium and chlorine. However, not all ions contribute equally to the resting membrane potential. The ions that are most permeable to the membrane contribute the most to the overall membrane potential. Pay attention to this next slide. As you can see, it is permeable to potassium only. Now, answer the 3 bullet-pointed questions below. In your head, you should be able to answer which direction will potassium move? Which direction will chlorine move? What is the final concentration of potassium of side A? Again, answer these questions in your head and you should be able to do them on your own. This slide gives us a great example of an ion's equilibrium potential that will affect the overall resting potential of the cell. In this situation, the membrane is permeable to potassium only. Pay special attention to the concentrations on each side, A and B. A few potassium ions in this situation are forced through the membrane by the concentration gradient, leaving chloride ions behind unneutralized. These unneutralized chloride ions is where the electrical gradient is created. The layer of positive charges on side B repels the potassium ions and prevents further diffusion. This is where the equilibrium potential is reached. To calculate the overall membrane potential, we will use the GHK equation. In this equation, you will multiply the equilibrium potential by the conductance. The conductance is a measurement of how permeable an ion is to the membrane. Remember, not all ions are equal permeable to a certain membrane. Conductance measures this. In this situation on this slide, we can see E sub K represents the equilibrium potential of potassium multiplied by the conductance, which is G sub K. Now once you have that figure, you will add that to all the other ions that are permeable to this membrane. In this situation, we see E sub Na, or equilibrium potential of sodium, multiplied by the conductance of sodium, G sub Na. You will divide this number by the conductance of all the permeable ions. In this slide, you see G sub K plus G sub Na, or the conductance of potassium added to the conductance of sodium. This is how you calculate the overall membrane potential of a cell. Now that we've explained the GHK equation, with the person sitting next to you, work through this problem which asks about the overall resting membrane potential of a cell.